In a time when an electron was thought to have a predictable electron structure, a brand new discovery was made. Previously, an atom was thought to contain a positive nuclear core, with negative electrons buzzing around ringed energy levels. In today's era, we know and can prove that these electrons more accurately exist in clouds and are essentially impossible to pinpoint the precise location. It's been a known fact for a great deal of time that electrons contain a negative charge, while protons have a positive charge. This truth explains how an atom can exist as multiple different ions in order to stabilize itself, while also bringing relevance to the whole world of ionization energies and electronegativity. But what if there was a particle that counteracted an electron? A particle that had the same mass as an electron, but precisely the opposite charge, a positive charge. In 1928, a physicist named Paul Dirac created a theory that such a particle could exist. Well, 4 years later in 1932, the existence of this particle was controversially proclaimed by a young physicist attending Caltech named Carl David Anderson. Hi there, my name is Ethan Lyons, and I sure am ready to dig into the discovery of the positron. Are you? Now, the average person may look at the word positron and immediately dismiss it as being over their head. My goal in this documentary is to explain how the properties of the positron can be understood through its discovery method and further research. During Anderson's time at Caltech, he worked extensively with a device known as a cloud chamber. A cloud chamber has the ability to study the properties of particles in relation to the physical matter state of the cloud. Now, there appears to be an obvious question on the mind of the audience. Keep in mind, that's you. How exactly do you create a cloud in a chamber? I thought that they only existed in the sky. In order to form a cloud, the compacted chamber is filled with water. A sudden expansion in volume inside the chamber creates a nice cloud, since the increase in volume leads to a decrease in temperature of the water molecules. Only under certain conditions can this cloud be used to study the properties of other particles. A great example of this can be seen when studying ions. In order to accurately study ions that are fired through a cloud, a certain critical value of chamber expansion must be met at a precise time. If this critical value is met and held constant, you simply get the formation of a cloud. However, if this critical value is not met, and the chamber expansion value is just below the critical value, a unique moment in time occurs. While there is no physical formation of a cloud within the chamber, a subatomic particle being fired through the chamber will cause tiny water droplets to form a line behind the particle path. This is because the high speed of the subatomic particle knocks electrons off of gas particles in its way. When electrons are knocked off of a neutral atom, the atom becomes an ion. Interestingly enough, when two particles exist in a cloud chamber, one being a neutral molecule and the other being a charged ion, the droplets of water vapor prefer to condense around the ion. This fact has been cited many times to give a reason for why clouds form around ionic centers. Anderson took this information and was tasked with the project of constructing a magnet cloud chamber, a device that would have the ability to study electron properties in cosmic radiation. Since cloud chambers had the ability to be used for subatomic particle research, the addition of a magnet to the chamber could produce the desired results. Remember, this research was conducted within the early 1930s, so many materials that are readily available today were not so prevalent then. This only makes the construction of a new magnet cloud chamber all that more impressive. Essentially, this magnet cloud chamber consisted of a cloud chamber inside of a magnetic field. Due to the large size of a cloud chamber, the magnets being used to attract the subatomic particles had to be incredibly strong to get the full effect throughout the cloud chamber. When a cosmic ray, a glob of high-energy particles, is shot through the cloud chamber, some subatomic particles traveled in the expected direction towards the positive plate, but a large amount also traveled towards the negative plate. The electron was already known at this point, but the existence of other particles shooting in the opposite direction could not be explained. Anderson managed to get excellent photographs of the trails left behind these particles, which would later be used as proof of their existence. Many other scientists criticized his research as mistaking the new particle for a regular old proton, but the track distance of a proton would be much shorter than that of an electron, since a proton has a larger mass. In this specific case with this experiment, the paths for the expected electron and the new particles were roughly equal in size. Before I move on, let's pause for a quick moment and reflect on what we currently know about these particles. The experiment shows that there are two groups of subatomic particles that are being produced, one group being negative, as expected, and one group being positive. These particles also have the same mass as seen by the comparison of the droplet trails behind these particles. Now, let's get right back into it. Anderson was now put in an interesting position where he could give up with the research and move on, or actually figure out what on earth those particles were. As any self-respecting person would, he continued on with an innovative way to fully prove his theory that this was, in fact, a brand new particle. How would you prove the existence of a new particle given these results that Anderson obtained? Would you A, ask other friends for help, B, fake data and present this to the world, C, spend countless hours diving deeper into research, or D, both options A and C? I'll give you about 5 seconds. Have an answer? That's right! The correct answer is B. I'm just joking. Anderson took options contained within the answers A and C to fully advance his experiment and prove this existence. In order to fully understand the direction that these particles were traveling in, Anderson decided to use a lead plate within the chamber to prove that the positive particles were in fact traveling upward towards the negative field. A lead plate would be able to help with this discovery, since any particle traveling through a lead plate would have a lower energy on the other side, and therefore the direction could be known. After Anderson entered his plate into his magnet cloud chamber, he did his experiment again and found that those new particles were traveling upward, since the energy was lost when they went through the plate. Take this picture for example. The path of the particle below the lead plate had a greater slant compared to the droplet path of the same particle exiting the lead plate, which had a smoother and less intense curve. This therefore proved that the new particles were traveling upward towards the negative field, which meant that they had to have a positive charge and the same mass as an electron. The positron had been discovered. The initial response from other scientists was not the most encouraging. Hey guys, after several months of research, I discovered the positron.
No, you did not.
The accepted theory was that all particles shot into a magnet cloud chamber were supposed to go in the downward direction towards the positive field, and only very rarely would a particle shoot upward. Anderson was able to replicate the same experiment over and over again so that he could prove this occurrence was not rare, but actually as common as that of the electron shooting downward. Since Anderson was able to show that particles going upward were no accident, but actually a common occurrence, he discovered the existence of antimatter. Anderson believed that since these positive electrons existed, they were the opposite of an electron. Interestingly enough, a positron cannot exist in the presence of an electron for more than a billionth of a second. So what's the point of its existence? When a positron and a normal electron come into contact with each other in a vacuum, they undergo a process known as mutual annihilation. This just means that their energies and charges cancel each other out, causing the destruction of both particles. This process begs one question. Does the disappearance of both particles create a vacuum in the space that the particles once existed in? Try the question on your own and attempt to create a reason behind the answer. I'll give you about 10 seconds. got a 50-50 shot. Well, your reasoning might be wrong, so I suppose it's trickier than that. The correct answer to the question is actually no. While mutual annihilation leads to the disappearance of an electron and its counterpart, particles of light known as photons are actually created. Photons are a kind of gamma radiation that exists within our natural world. There is definitely something to be said about a particle that rarely exists on Earth being used in the creation of a particle being the photon that is natural and pretty common on Earth. There are current theories that there are universes out in distant space that are completely composed of antimatter, which makes our normal matter irrelevant in the perspective of that environment. This would mean that the positron could actually exist for longer than a fraction of a second in the absence of normal electrons. The positron may only exist for a fraction of a second in our world, but there are actually some pretty ingenious practical uses for such a particle. Among these uses is a medical system called the positron emission tomography scanner. Such a system can produce images of organs within the body, which is extremely useful in diagnosis processes. These images can be used to detect certain cancers, different heart conditions, and various processes within the brain. The positron emission tomography scanner works through emitting radionuclide, which are rich with positrons, into the human body. These positrons are then annihilated by normal electrons and will therefore produce photons, which classifies as gamma radiation. This gamma radiation is then reflected back into an imaging system that makes sense of the pattern of photons sent back and produces an actual image. It's quite interesting that the discovery of the positron led to the creation of a medical system that can help diagnose patients. The discovery of the positron by Anderson was the first step into the new world of antimatter. Since then, the antiproton and the antineutron have been discovered in the years 1955 and 1956 respectively. These particles were discovered in a bevatron, which is a particle accelerator capable of generating about 2 billion electron volts. In the simplest terms possible, an antiproton is created by smashing two protons together at such an immense speed that one of the products involved is an antiproton. The existence of these antiparticles proves that for many subatomic particles, a complete opposite form exists. The uses for such particles are constantly expanding. We are still very far from completely figuring out all of the properties of antimatter, but that mystery and wonder keeps our world curious. Besides, some things are better left unknown and undiscovered. As Carl David Anderson said, apparently the Creator does not favor a world of great simplicity.